matrices, well, just square matrices. And today I'm going to be talking about non-square matrices. Okay, but before I get to the overall non-square matrix, I'm just going to cover a couple review things and a couple new topics. So when we use our vectors, and I'm actually going to start going into 3 dimensions now because a lot of non-square matrices require the use of 3 dimensions. So any vector v in 3 dimensions is now, and let's say that this vector v is a, b, and now we're going to add another row, c, which is the same thing as saying a times I plus b times j plus c, and now we have k as our new unit vector in 3 dimensions. So it's the same thing as we talked about last time, just adding another spatial axis here. Okay, so last time we talked about matrices, we talked about like 2 by 2 square matrices, and so they look something like this. So I'll call this matrix A. A is A, B, C, D, and right here is where I hat lands, and right here is where J hat lands. This is all just review. Okay. But now I'm actually going to show how to compute something with the matrix itself. So
wait,
yeah.
sorry, why is it like A, B, and C? I feel like last time was X, Y, Z. Does it like matter? Or, like, what's the reason? What's the rationale?
X, Y. There's no reason. I just have random letters. It could be any random letter. Yeah, I probably should stay consistent with that. Okay, so I'll give an example, and I'm gonna write this out. So suppose we had a matrix A, so this is what describes our transformation. And we have like 5, 7, 3, and 4. Okay, and I want to see after I apply my matrix, I have a vector before the matrix, which is 2, 3. And I want to see what happens to this vector after I apply this transformation. So if we remember, we can write 2, 3 out as vector 2, 3 as 2I hat plus 3j hat, right? That's just what we did last time. But now, and so here's what we're trying to find. We're trying to find A, B. So this is our matrix. This is the notation for our matrix applied to our initial vector here. Okay, so here's how we write out B is 2I hat plus 3j hat, which is what we did last time. And here's our matrix A. And we take a look at our matrix A, this is where I hat lands, and this is where J hat lands. So we can write our new transformed vector as 2 times I hat prime plus 3 times J hat prime. That's what we've done here. Is instead of saying, okay, it's a composition of our normal 2 unit vectors, it's now made up of our 2 transformed vectors, and that's how we find transformed V. And so transformed V in this case would be 2 times, and here's our transformed I, right? 5, that's where I lands. And it would be plus 3 times 3, 4. Okay, and now if we just write this out, this is what our scalar rules like we did last time. This is equal to 10, 14 plus 9, 12, which is equal to, and I'll write it here, 19, 26. Okay, so this right here is what happens to vector V after we've applied the transformation A. Does that make sense? Okay.
Yep.
So that's essentially what we're doing, is instead of saying multiplying by I and J, we're multiplying by I prime, J prime, which is our new and transformed I and J. Okay. So that's just like wrapping up the previous lecture. And now what we want to do here, now what we're going to do is we're not going to just look at stuff in 2 dimensions. We're going to look at stuff in 3 dimensions. So now we have K as our unit vector along the z-axis, which, and I'll write this out. K is 0, 0, 1. Okay, so here we go. Okay, so last time we talked about transformations, and we're just like rotating and stretching and doing whatever with our vectors, right? But we can also do other things with our vectors. We can actually have a transformation, but also have it go from one dimension to another dimension. So let's say, I'll give an example here. Let's say I had, I had 2 dimensions here. And here's J, and here's I. And let's say I wanted to apply some transformation to J and I, and I'll call this transformation A as usual. And let's say I wanted to say, wait, let's say I wanted to have J and I all of a sudden be squished onto a line. So here's I, and here's J, for example. And I stretched one of them, whatever. Let's say I want to basically squish all space, and instead of having it in 2 dimensions, we all of a sudden, all of our points lie on a dimension, right? We can actually, and here's another example. What if I had the same thing, and I had J, and I had I, but now, what if my transformation A, instead of squishing it onto 1 dimension, what if it extended it to 3 dimensions? So now I lands like somewhere here, and J lands like somewhere here. And so these are transformations that we can still describe using the matrix, except now we're not using a square matrix where the rows and the columns, they have the same number of rows and columns. We're using what's called a non-square matrix. So I'll write this down.
Wait, but
Yeah.
if you just have it in terms of I and J and you don't add an additional variable, then it wouldn't really necessarily matter that it's in a 3-dimensional axis, right? Because it would just be still a plane, right? I mean, if you have no vector that.
I can show you why that would be the case.
Oh, because you can have it like angled in a certain way and like.
Yeah.
Or like.
This makes sense, right?
Well, yeah.
Okay, this one right here, I'll go more in depth.
No, I'm not saying I don't. I'm just saying like, if you don't have a third variable, like why is it? What's the advantage of having a third plane with just 2 variables? Is that?
There's no advantage. What all this represents is just that we have 2 dimensions that now go into 3 dimensions. So if you look at this, if you look at the new and transformed J and I, they actually have a K component themselves. Or else it wouldn't be possible to go into 3 dimensions. So yes, they do have a K component.
But it's just like a constant K component that doesn't change, or like?
No, the K component does change, and I'll show you why.
Oh, but then there is 3 variables then at that point, right?
No, I'll show you exactly like here. I'll write this out, and I'll go to this one first because this is the most important one, and then I'll go to the next one. Okay, so non-square matrix. Okay, so the non-square matrix is just a matrix that doesn't have the same number of rows and columns, so it could have like, it could look like this 1, 2, 3, 4, and this would be considered a 1 by 4 matrix. Or we could have like 1, 2, 3, 4, 5, 6. This would be a 3 by 2 matrix. Okay, these are just examples of non-square matrices. So, and I'll jump to this one right here. So how would we describe a transformation like this, where initially we have 2 dimensions, and all of a sudden now we're up to 3 dimensions. Okay, so right here, so I'm gonna write out my matrix. So this is my matrix A, and matrix A has, and here's I and J, right? Okay, so we agree that when we write our matrix, the rows tell us where I and J land, right? Like where I, J, K, all of our unit vectors land, right? Or sorry, the columns. So if we had a matrix, and we'll call it, I don't know, I'll have A, B, C, D, E, F. This is what our matrix looks like.
Yeah, because it's like the endpoints, right?
Yeah, exactly. And so initially I and J, this had points, what is this? 0, 1, and 1, 0, right?
Mm-hmm.
But now I
yes, is that because you're adding the K component? Or?
exactly. So I has a K component.
So the C and the F are basically like the
scalars for K component.
Yeah.
Yeah, within I. So they do have K components within themselves, but in order to write a transformation from 2 dimensions to 3 dimensions, we still have to keep only 2 vectors, or else we don't know how many dimensions.
So you just add basically like a third variable in the vector.
Yeah, exactly.
That you described.
So C and F now tell us how far up we're going along the z-axis.
Also, then there's basically an extra variable. It's just not shown like that, I guess. Because like normally before it was like just 0 and 1, right? So then basically if you have 2, and then now you're adding another one that is a certain number, so it's basically.
Yeah, but it changes depending on the vector that you add.
So it's basically like adding a third variable, but still describing it in terms of 2 variables, so that you can transfer it.
Yeah, exactly. Yeah, yeah. So yeah, you're adding more constants to the end to describe, okay, what is our shift in the z direction, which is k.
Yeah.
Okay, so this is how we would describe like a shift from 2D to 3D. And the actual notation behind this is written as A, which is our matrix, is, and here's our A, and here's where it's gonna, I'll write this out and I'll explain it. Goes from r squared to r cubed. And all r squared and r cubed represent is our vector space, and so r squared is a 2D vector space, r cubed is our 3D vector space. So this is what it's saying. It's saying that with the transformation A, we initially are in r squared, which is 2D space, and we now go to r cubed, which is 3D space. And yeah, and that's so this is a 3x2 matrix, and so a 3x2 matrix represents a transformation from 2D to 3D. And so if you wanted to represent a transformation from, let's say, 2D to one dimension, which is just our line, this one would look a little bit different. So right here, right, we initially have, we still have our 2, so that this is basically the number of columns that we have represents the dimension, like the initial dimension that we were in. So right here, we were initially in 2 dimensions, and now the number of rows that we have, we're now in 3 dimensions. Okay, so if we wanted to describe something like this right here, right? What we would say is our matrix, and I'll call this matrix like L. Matrix L, so this is our transformation L. Matrix L, this is what matrix L looks like. It just looks like A, B. So here, this is where I hat lands. This is where J hat lands. But notice how there's only one, that there's not 3 axes, there's not 2 axes, there's 1 axis. One direction, or 1 axis where they can be described where they're going. So A could be negative, A could be positive, and so this is essentially what describes our transformation from 2D to 1D is now I hat just has a singular value, A. It's scaled by A, left or right along this axis, and J hat is scaled by B, or left or right along the axis. And so we can have, so we can have transformations. We can even go even further. We can say, I want to go from 1 dimension to 3 dimensions. I want to go from 3 dimensions to 1 dimension. I can go, yeah.
Wait, what's like the advantage of having it in terms of like 2 variables? Why couldn't you have just had like just I, and then had a starting value that's there, and then the ending value, instead of just?
Oh, yeah, I see what you mean. Okay, so yes, technically, if only I, right? I agree with you. Only I determines how stretched or squished our axis actually is, right? But this J right here tells you. So here's the thing. The reason why we do this is because our initial vector that was initially in, like, let's say we want to transform some vector v over here. this is some vector v that we're looking to transform.
Yeah.
Our initial vector v is made of j and I components. So if we just take out the j component, even though I represents the axis that we're sitting on in the first place, j is a really important part of this vector initially, and so we can't just ignore that. So if I wanted to say like I want to say LV, what is LV? Well, I would have to say, okay, well, it would be, what is this? V is, I'll call it XY. So what V would look like, and so we have hold on, sorry. I'm gonna have to write this out. This is gonna take a while. I'm gonna have to write it out like back here. But anyway, you see the whole point is that like you can't ignore this because even though J and I sit along the same axis, V is made of J, and so that changes the direction in which V is pointing. Okay. I think that's pretty much it for today. I think I'll go over one more example, but we're running out of time anyway. Actually, I think that's it. Yeah. So in general, I think so. Yeah, we want to make sure that when we look at our matrices, the non-square matrices in particular, the number of columns determine what our initial how many axes we had initially, and then our rows are how many axes we ended with, and that's pretty much it.